So hi everyone, my name is Shangar and in this video we are presenting about Belief Network. As a group number 13, we are a team of 4. There are 4 members that are Harshit, Deepak, Shanu and Shubham. Let's start. So next, in this video we'll be presenting the whole presentation in 7 parts. First part is about introduction, I'll be leading this. Then Shubham will tell about Boltzmann machine, followed up with Deepak who will tell about RBM. Then Harshit will tell about DBN. Then we will go to rest of parts and I'll end the presentation. Next. So this is our base paper. This paper was published in 2006. It was proposed by Geoffrey E. Hinton and Simon Ozindro along with Yi Wai Teh. So basically, first I'll be telling about the history, how we started and why we need Boltzmann machine, restricted Boltzmann machine and why we need DBN as a glimpse, and then Shubham will start. So first we had a normal squiggle fitting algorithm that was backpropagation. But due to some problem like vanishing gradient and a lot of steps, learning ratio and all that, it was getting problematic. So to overcome the vanishing gradient problem, the model of Boltzmann machine was proposed. In this, we have a simple network that is such that every node is connected to every other and it's quite complex. So after this, the another model of RBN restricted Boltzmann machine was introduced in which node to nodes of same level can connect, and then the step of RBNs form a deep belief network, and then it has many layers of RBM, and then we get some classifications of types of input, and then we label them to get final result. Over to Shubham. Thank you.
Yeah, thanks, Anu. So basically, I'm starting with Boltzmann machine. So a Boltzmann machine is a type of stochastic recurrent neural network, and it's basically invented by Hinton in around 1980s. So more clarity, what I can say is, in the words of Hinton, a surprising feature of the network is that it uses only local available information. The change of weight depends only on the behavior of the two units of connections, even though the changes optimize a global measure. Some important points which I can infer from the Boltzmann machine is they use recurrent structure. They consist of stochastic neurons, which have one of the two possible states, either 0 or 1. Some of the neurons in this are adaptive free state, and some are clamped. And so, basically, coming to the objective of Boltzmann machine, the main purpose of Boltzmann machine is to optimize the solution of a problem. It is a work of a Boltzmann machine to optimize the weight and quantity related to that particular problem. And as you can see in the slides also, nodes present with same bias to make binary decision, and also there are input layer visible and there are hidden layer also. And as you can see from the equation which is mentioned in PPT itself, this method is used when the main objective is to create mapping and learn from the attributes and target variables in the data, where energy can be defined as the equation which is mentioned in PPT, where all the variables can be defined as Wij refers to connection strength between units I and j, and Si states the state of unit I. Theta I basically represent the bias of unit I in global energy function. This is all about Boltzmann machine, and after that, Deepak will continue about restricted Boltzmann machine. Thank you.
Uh, Thank you, Shubham. So in this PPT, I will talk about restricted Boltzmann machine. Basically, in this slide. So the key difference between the Boltzmann machine and restricted Boltzmann machine, we are going to discuss in this slide. So the key difference is that in Boltzmann machine there is a interconnected nodes. Means there is a node between, there is a edge between a hidden layer and a visible layer. But in this case, in restricted Boltzmann machine, there is no interconnected edge. And moreover, basically this restricted Boltzmann consists of two layers, basically visible layer and hidden layer, same as Boltzmann machine. And this RBM observe real world pattern and is basically try to create a low dimensional representation of those pattern. Shanu, move to next slide. Okay, now we will talk about basically RBM training. Basically, this E of V, H, V, H Here we try to basically minimize the total score, and there the score which I call is basically summation of AIVI minus summation of BJHJ and VIHI into weights, where VI and HJ are basically the binary state of visible unit and hidden unit J, AI, BJ are basically biases, and WIJ is the weight between two visible layer and hidden layer. Now, basically, this RBN training is basically similar to training of feed forward neural network. First, the data is passed from the visible layer to hidden layer, and then backward passed from the hidden layer to the visible layer. Basically, after this train with back propagation. Shall move to next slide. Now we will discuss about the logistic belief network. Basically, logistic network is similar to RBM. The undirected edge are replaced by directed one, and basically they form a acyclic graph. Basically, in the RBM there are directed edges, but in logistic bleak, undirected in RBM, but in case of logistic bleak network there are directed graph, and it is a acyclic graph, and that means and there is no any cycle present in. The main concept in this is that there is a node J, and the turn on condition basically depend on the its parents. So this is all about the logistic belief net. Now from here on, Harshit will take over. Yeah,
Yeah,
shall
thank you,
move
Deepak.
to.
So, up till now, we have seen what Boltzmann machine are and restricted Boltzmann machine are, and after that, Deepak also talked about logistic belief nets. So now we'll see what deep belief networks are and how that the knowledge of Boltzmann machine, restricted Boltzmann machine, will help in studying about deep belief networks. So as you can see, deep belief network is a stack of RVM on top of each other. In this figure on my left, you can see this is how a deep belief networks looks like. The nodes that are marked with a circle are actually probabilistic nodes. That means they depict the state whether they are on or off, and you can see that this these layers actually form an RBM. And even in the base research paper that we have took, they also worked on performing the inference in deep belief networks. And in order to establish that, they came up with a new learning technique so that they can accomplish inference from deep belief networks. What they did was they took adjacent layers at a time and trained it with the RBM learning rule. As you can see on the image on the right, if I have say an L layer DBN, the nodes within the layer are not shown. Only the connection from one layer to the next are shown. So what these researchers in the base paper did was they took these two adjacent layers and marked it RBM1, and then in the subsequent layer they marked it as the RBM number 2. So in total there will be L minus 1 RBMs that will have to be trained. Before we talk more about the training, how that's done, I want to talk more about the structure of DBA. So in this figure, you can see that the top two layers have undirected connections and form an associative memory. The This symmetric connection is in this figure decomposed into connection that is going from top to bottom and one that is coming from bottom to top. The layers can be seen as it mentioned in this diagram. They can be seen that ones are outlined directed edges that are going from bottom left to the top. These will be used for the greedy learning of the deep leaf network. Their edges going from top to bottom that will be used for generating the image from the associative memory. So there will be two parts of the training of the DBM. During the bottom up training, the top level RBMs learn from the layers below, and during the top down generation, the top level RBM will be the initiator of the generative modeling. So you can see this that the DBM structure is actually a hybrid of RBM and logistic belief net. Now, now looking up into the bottom-up training. The layer-wise training is actually a greedy approach, as the hidden layer for the first RBM will act as the visible layer for the second RBM, whose hidden layer will act as visible layer for the third RBM, and this process will go on. So a subsequent layer will actually learn the features of features. Actually, these techniques were developed because of limitations of backpropagation, namely the problem of vanishing gradients. Once the DBM is trained with the greedy algorithm, the weights that are learned will be fine-tuned by using backpropagation. Now, once we have trained the model, we want to see when we want to use the associative memory that was sitting on the top. We will take this approach. An equilibrium sample, yeah, an equilibrium sample will be taken from the top level RBM by the Gibbs sampling technique. Uh, how this process will procedure can be seen in this chain of events. So at some time zero, the associative memory will be set free, and its effect on the hidden layer will be seen. And it's the hidden layer will then try to generate back what it would generate back at the visible layer, and this process will keep on continuing. And after uh, some time when the associative memory has reached equilibrium, we'll take the sample. Now, once you have got the sample, a top-down pass starting from the visible layer of the top level RBM will give us the generative example what the model thinks. The algorithm for training or debugging can be summarized and in these steps. So first we take the training data. It is a n-dimensional vector, and say our deep belief network has L layers. Then for the first layer, we don't have to do anything, as the visible layer will be simply the training data that we have given. And in the subsequent layers, what we have to do is we have to take two layers at a time, and we have to train them using the RVM learning rule. And we'll keep on continuing this. And once we have done this for all the RBM layers, we'll have learned the weights and biases. Now, once you have learned these weights and biases, we'll try to fine tune them using backpropagation. And now, Shubham and Shanu will explain explain some real time examples and talk about what's the future for deep belief networks.
Yeah, thanks, Sarsit. So basically, the real time, some of the real time example of deep belief network, as you can see, are natural image processing, natural language processing. So basically, what natural language processing is, so making computers understand the natural language. So that because computers can understand the structure form of data like spreadsheet and tables in the database, but as a human language, text, and voice form an unstructured category of data, and it's get difficult for the computer to understand it. And there arises the need for language image processing for processing the data into small chunks. There is a lot of natural language data out there in various forms, and it could get very easy if computers can understand and process that data. We can train the model in accordance with expected output in different ways. Humans have been writing for thousands of years. There are lots of literature piece available, and it would be great if we make computer understand that. And for natural language processing, so there can be some of the step. So first step can be sentence segmentation, breaking the piece of data in various sentences. Second step can be word tokenization. Third step can be predicting parts of a speech for each token. Fourth could be lemmatization, and fifth would be identifying stoppers, and sixth can be dependency parsing. So there can be these type of step, and they can be increasing according to our need. So this is basically a gist of the natural language processing. And other than that, there is image compression, one of the uses of deep neural network. The compression of images is carried out by an encoder and output a compressed form of an image. In that process of compression, the mathematical transform plays a really important role. A flowchart can be seen as an internet also, or you can see anywhere if you want to get a deep dive into it. So these are the basic idea of the real-time example, and there can be many example out there, but these we have covered in this particular PPT. You can see on different links, or you can figure out yourself also. So from now onwards, Sanu will take over. Sanu, you can start.
Thank you, Shubham. So, after understanding the basic application, or I would say major applications of deep belief network that Shubham just mentioned, I will talk about the future work of this model. So after some time, we are expecting that deep belief network can be used for various important tasks that include human emotion recognition, as I have mentioned here, and a part of it we can also automatic liver segmentation is another thing which can be obtained by deep belief network. We can also learn features from music audio with deep belief network, as we know that there are many musicians but there is some pattern in the music they propose or they compose, so we can also find features out of them. And a part of all these things, we can also predict the resource requests in cloud computing environment, which will help in getting quick responses for upcoming fast internet time. Next. So these are references we use. First one is our research paper. Then we used some Google Scholars text for getting the all things in future work. There is in the next link for book and some other links we use for getting all this information. So this is all. Thank you so much everyone. I hope this video makes sense and make you understand a little more about deep belief network. This is a presentation by group number 18 in presentation and group number 13 as in class. Thank you so much. See you soon. Thank you. Bye.
Please leave your comments below so that we can know how to improve.
Yes.
Thank you very much.
Thank you everyone.
Thank you.